Let's see if this gets going. Then we can share it and then... Whoa! And we can share it and then... Whoa! There we go. All right. Let me get this shared and then we'll go pick up where we left off. So, okay. All right. So, hopefully Twitch works this time. Let's see if it does. Twitch maybe works. Maybe it doesn't. Twitch continues to not work. All right. Deal with that later. I think we're working on YouTube. So really, it's YouTube and X that I care about right now until Twitch figures their stuff out. Okay, so we are going to continue engineering this pendulum. We're almost done, but I, in a fever dream, realized last night that I made some mistakes. So we have to rectify those. We will rectify those. They are related to the encoder here. We also, I forgot to attach the encoder to the first to second pendulum interface, which shouldn't be a big deal. I don't think it will be. And then we will lighten this up a bit because I think mass actually matters here. You can see that I already got started here on the bottom. So we're going to do all of that. So let me tell you what's going on with this encoder. I realized that this is critically spaced. So this is the magnet for the magnetic encoder. And this is the PCBA for that magnetic encoder. They have a set distance they have to be, which is roughly 1.28 millimeters. It is so critical, in fact, that the manufacturer actually includes a spacer to use during installation. So, what does that mean? It means that this distance here to here is critical. And really the right way to do this is to set up a critical tolerance stack, determining critical datums within these parts to build out the distance between these two. What would that look like? Well, it would first look something like radial position based off of this locating feature here, which would set the X and Y. Z is axial. So that would probably matter, but let's look at just Z here. So what would determine that? Well, when this part gets machined, this surface here to here would be critical because that defines where it sits in the assembly. Additionally, the thickness of this flexure also sets that distance. Finally, you get, well, not finally, but then you keep going. Then you go into this holding arm, which sets the bearing, which then sets the outer to inner ring distance, which then sets this nut on a thread, which then sets this. All that to say, if I run the tolerance stack on this, it's going to be all over the place. Like this is going to be plus or minus probably like a millimeter. It's going to be crazy, which is, 75% of the gap itself. In addition to that, I'm not totally sure that the FEA we're running on this flexure is accurate enough to say that 3.2 millimeters is really what we need. So it might be that I actually have to come back after the build and change this to 1.6. And then I'm gapped, right? So there's a lot going on. And I could go do the tolerance stack, right? That would be the right way to do this if this was productized. If I was going to go make millions of this thing, that's what I would do. But I'm not making millions of this thing. I'm making one. And so instead of running the tolerance stack and doing all of that, what I could do is instead find a way to mount this so that it really doesn't matter how much that tolerance stack ends up being. I can just position this with that spacer and just dial it in correctly. So that's what we're going to do. And so looking at this, I originally thought, well, I might actually use washers between this part and this part. And what I'm realizing is that that's actually probably more complicated than a simpler solution, which would be to push the assembly back and then add adjustability here. So in other words, give myself, some space on this side and some space on this side. Then I use that spacer they include with the encoder. We put it in and then we call it a day. We tighten the set screw down. I think that's the path we're going to take now that I'm talking about this out loud. And by the way, if the background noise is bad, let me know. I'm trying to run this without any filters because none of them have really been working well. So that's where we are. So looking at this, I think the solution is extend this shaft, push all of this back, and then we will give ourselves, we'll call it 3 millimeters on each side of adjustment. The reason I say 3 is because we might gain or lose a couple millimeters here in the thickness of this plate to dial in the preload here. Really, I really should be kind of separating this, the functionality, but I really do like how simple that design is. And we needed adjustability here anyways, so I'm not too concerned about that. So why don't we go ahead and make that change. So let's say we want 3 millimeters backwards and forwards axially, or in Z, which is actually X in this coordinate system. So what I'm going to do is just move it essentially 6 for everything on the left, and then 3 for the actual magnet. And it's really as simple as just picking this stuff up and moving it. All of the non, well, yeah, I think it's that simple. Yep, I think that's it. So we're going to move this back 6. And then we're going to pick specific faces here to do that because I want to maintain this distance here. So I'm just going to move these faces of that part. That's 6. Okay, so now that distance broke, right? So we have to fix that. Before we do that, let's actually adjust this shaft. So we want to give this 6 millimeters. Okay, and then finally we move the magnetic encoder. They call it the target. I like that name. We'll move that 6. And actually, what we do is we move the encoder back 3 because that gives us the 3 on both sides. So let me do that. And I should double check those screw distances. This will have to come out 3 to accommodate that change. Actually, is that right? Because this is going to be fixed. Yeah, that's going to be fixed. Might have thought about that incorrectly. So we came out 6. We get, this is at the, sorry, we actually want 3 on this side. Yeah. Because we want 6 to adjust this out and back, right? So in other words, if this is too close, we back this out. And if it's too far away, yeah, I think we only needed 3 there. So, and I need to extend this 3 in case this is off. Yeah. So this comes out another 3, I think. And that shouldn't be an issue. Actually, what I need is just to make sure that I have roughly 3 here. So if I move this 3, does that work? No. So I actually need to move this just a little bit. Call it 2 to maintain to ensure that I always get engagement with that set screw there. And as a matter of fact, we should machine a flat into this. I think that's actually going to help with location. Yeah, we should do that. And then finally, I think I have to undo that move. Yeah. Okay. So this means now that I can move this. If this is nominal in CAD, I need to be able to move this 3 millimeters this way, which I'm able to do. And I'm also able to move this 3 millimeters this way if I need to. And then we actually can move all of this now back 3 because I didn't need all of that. So I did this in, I was thinking about this incorrectly earlier. So let's do that. So that goes back 3. This face comes back 3. And then this comes back 3. Okay, so now I can move this. If I move this 3, I actually don't collide with this yet. So perfect. So let's add a flat to this shaft actually, now that I'm talking about that. And that's just going to help that set screw sit nicely. I'm already anti set screw, but this would make me feel better about it. So let's see, we want this view. And so we'll give this, I don't know, just like maybe a millimeter of flat. Don't really have any science to this. Yeah. Let me pull that through. Now, we don't want to pull it all the way. We want to add some relief there so that way they can actually machine it. We'll give it, say, 7 millimeters. And then what we'll do is we'll make sure that when I pull the set screw back 3, it still engages properly. So if I move this 3 in the worst case, no, we don't get the right amount. So we actually want to pull this back more. They might come back and complain about this. I don't think they're going to turn it, so I think we're okay. But let's see. Yeah, let's try that. I mean, honestly, let's just see what they say in the DFM. I'll address that later if I have to. Actually, it does matter how much I give. So 1 millimeter is probably the maximum there. So that's good. And then we want to delete that move that I just did. Yeah. Okay. So that was easier than I was expecting. We got our adjustability there, which is good. So Let's see. Okay. Now we have to add this encoder here. I'm going to quickly pull out that encoder. Now, how did I do this? I think I did it with a custom nut here. Actually, we might be able to copy this design, which would be awfully great. Yeah, as a matter of fact, I might be able to just copy this design. Now that I'm looking at it, I do think we have to get rid of this nut. So let's see. I think we copy the encoder, we copy the nut, we copy. We don't have a slip ring, so this actually simplifies a bit. Actually, I think this part's gonna be different enough that we don't copy that. Yeah, so let's play with this, see what we can do. Okay, so I'm going to copy really it's just the nut and the encoder. So let's try that. We want to pick up the inner ring of this bearing. Double check that that landed correctly. And it does. We need to increase the OD here. Actually, that OD might be a problem. Actually, the diameter of this nut might be the problem, which would be disappointing because I would like to reuse this nut. And I might have to delete, I might have to make a second nut, or if I'm lucky, I might be able to salvage this. So first things first, we got to bring this back. Okay, and then this diameter is a little too much, so I think we actually have to go back and fix that. And I don't know that we have a hard requirement on that nut being that size. Yeah, so we can actually quickly adjust both. So if we come back here, we can quickly just adjust this diameter. Let's see if that is easy enough to do. So let's take away 2 on that. Plenty of meat there. Let's go for 3. Negative. Okay. And now when we walk back, that should probably get here, and it does. That sits nicely on the inner ring, which is inspiring a little confidence. We still want the adjustability here. So now we have to mount this, which we can pretty much just kind of copy that. What are you? What's... Yes, I use my VM for video games. It's good that it's popping up. Oh, I should reopen that as sim real quick. I forgot to actually check stress on that. And I also forgot to save that simulation result. So what was the stress? I think we're okay. We're not okay. That's super high, but that For aluminum, that's actually kind of expected. You get hot spots there. What this is telling me is we need to reduce. We need to increase the radius here. So it's looking like 3,000 MPa. Is that right? That's crazy. I should have looked at the numbers on this. Yeah, I should have looked at the numbers on this. Can I change the output? Let's see. I think MPa, if I remember, is just 0.15. Sorry, there's we've been getting hummingbirds stuck in our apartment, and they fly in and they don't know how to get out. And it sounded like one just did it. So I might have to go rescue a hummingbird. So yeah, what was this number? We can, so you can actually ignore a couple nodes here. We would check if this this mesh converges, or the analysis converges with this mesh, by refining the mesh and seeing where the values approach. So let's probe away from that. So we get 3,400, which is still way too high. And actually, now that I'm thinking about it, we actually don't care. No, we do care, right? Because if it plastically deforms, then we might not be getting the preload we think, which would be disappointing. Crap. Yeah, that's way too much. We need to reduce that. Crap. So we might have to fix that. So we're looking for 30 KSI, which is roughly 200 MPa, which is a lot less than this. I know why it's doing this. It's because we well, first of all, actually, what's the actual deflection? Because we want to make sure that's correct. Yeah, so actually, never mind. This is at way too much deflection. We're only going to do 1 millimeter. So let's go ahead and lower that load. See what that does. So we're going to go to 35. See if that still breaks. .42. How's stress? It's getting better, but not quickly enough. So we'll do 25. Rerun that analysis. I have to say, compared to my previous FEA tool, this is actually running much faster than I was expecting. It's actually running as fast. It's phenomenal. All right, so that's 1 millimeter. And we actually want U3 displacement only, right? Let's see. No, I think we want X. Yeah, we want U1. U1 is, 1 millimeter. And then stress is still, well, it's reducing more than I was expecting. So 1,700 times, I think it's 0.145. It's 250 KSI. It's still way too high, but we're getting there. If we reduce Actually, without having to rerun this analysis, I bet we can prove that if we lower this to 1.6 millimeters, we actually are fine. So bending stress is equal to MC over I. We know our bending stress right now is, what was it, 250 KSI, which is, yeah, 250 KSI. Let's keep it in MPa, actually. It's going to simplify this. So 1,700 MPa. MPa, which is actually e to the 6, I think. Yes, e to the 6, which is equal to m. That is this distance. Let's pull up that CAD. So from here to here, we're looking for z. Where's my deltas? Give me my delta z. Which is, call that 7.7. So that's 7.7 millimeters, which is this many meters, times the load, which was, I think we said, 25 newtons. And C is, actually, this is where now we have to derive this. So C is equal to thickness over 2. I is equal to BH cubed over 12, right? That's the second moment of area, by the way, for a rectangle. And it is 12, not 3. 3 is bending. No, 3 is for deflection. Okay, BH cubed over 12. And then H is actually T. It's actually T. B T cubed over 12. Right. Let's look at that again. Yeah, T. And so we plug this in. Well, actually, let's solve first. I don't know why I did this. So we'll actually bring this over and say that this is M, which is equal to 0.0077 times 25, which is 0.2. Yeah, so we actually want to plug and chug here. So let's do that first, and then we'll solve this out. So we have bending stress e to the 6 is equal to this, which is, we know M, times T over 2, because remember, C is equal to T over 2. Then we have this over I, and I is B T cubed over 12, which carries up to the top. So solving this gives us, this actually becomes 6, because you divide 2 into 12, 6M, and then T goes down, because we're going to take it away from there. 6M over BT squared. We're getting there. And so now we move this over and we solve for the new T that we want. And so T doesn't look like a T, it looks like a plus. t is equal to the square root, because we're taking the square root to get that second power out. And we're moving it up. So this comes up here. T is equal to the square root of 6 m over b times 1700 e to the 6. So let's double check this before we solve. So b stays where it is, t comes up, check, square root, check, 6 stays where it is, m stays where it is, 1700 e to the 6 comes down. Okay, so now let's write this out. We have 6 times m, which was point. I'm going to put this in ChatGPT, so I want to make this very clear. 6 times 0.2 over b, which is the width of this flexure, which is 6. Times 1700 e to the 6. Okay, let's see if ChatGPT can solve that real quick. I feel bad for the latex companies that have been transposing as a service scribbles and equations into LaTeX and vice versa, because they just got destroyed by ChatGPT essentially. So what this is going to do is it's going to tell us our new target thickness, which we're going to go to. We're going to go here and use the spec. Oh, it thinks it's time. So 0.343. That's actually way too small. That's way too small. I think we can just... Preload doesn't matter that much. I just made up the preload thing. What matters is that it locates it. So as long as it plastically deforms, that's fine. Because then it's going to plastically deform to hold it in place. We shouldn't overthink this. This is enough. This is enough. We're going to assume that it plastically deforms, and that's okay. We just proved that the install force was sufficient, so we'll leave it there. Okay. This distance is wrong, so we want to... No, this distance is correct. Never mind. Okay, so now we have to mount this. Can we steal any of the geometry from here for that? For instance, these mounting holes. I don't know. I live near a train track. In case you hadn't figured that out. And they're upset with someone. So I think we can steal this geometry. We'll just kind of copy it and steal it and play with it. Because this locating feature is going to be nice, and we probably want to hold on to that. Okay, got copy on. Perfect. We don't need this feature. We don't need these holes because we don't have that slip ring anymore. And are they lined up? Yes. Does it matter their orientation? Yes, because we want that cable exit to point down. Can we salvage any of this? Probably. That's what I'm going to do. I'm going to slice this and then try and manipulate this to get it in a good place. Actually, this is a bad idea. Do I get to cheat my way out of that? I don't think I do. So, man. All right. Using Shaper's new slicing with a sketch geometry feature. Be still my beating heart. Look at that. Just like NX. NX lets you do that. Can you believe it? NX functionality in a $40 a month solution. The best. SolidWorks can't do that. It's great. Okay, so we're gonna have to pick this feature up. And we're kind of held in place by the OD of this feature. So let's see how we would do that. You might see my wife. Hello, wife. What was that? Okay, bye. All right. So what am I gonna do? I'm gonna keep this geometry because I'm gonna slice this. So let's say we want a minimum of 3 millimeter thickness on this. So we'll offset this 3. Okay. That gives us our cup. And we might be able to get away with picking this up now. So this might actually kind of work. Let's pull a section real quick to sanity check that. It's tight, but I think it works. Oh, we have to cut a slot out here for the cable, but we'll do that in a second. All right, so let's draw. So I guess a good way to set this would be tangency, right? And I'm going to go on mute for a second. Okay, so I'm realizing now it's actually bad practice to use these screws to locate the encoder cup and this plate because it's going to be a pain to install. So I'm actually going to add another set of screws to simplify this. And so you're going to actually see me rotate this. And the reason for that is because of, well, it's for the reason I just said. Before we do that, I want to maintain the position of that encoder. So I'm going to slice this out real quick to rotate this. We're going to pull that 90. Actually, 60 would work. Is it 60? Yeah, 60. And very lovely. We don't actually interfere there, so this works out okay. And then we rejoin this. So that seems to work. I don't know what you are. Oh, yeah, we have to tap this. And that is tapped, actually, so we're fine there. We don't need this center hole because we are not passing any signal through. We do want to add that feature, though, to machine this out. Sorry, we want to add the feature to make room here for the encoder cable. So we'll do that now. Then we'll modify this deal. Okay. Yeah, you can see there it's trying to protrude. So this is going to be tricky because this is a round surface. Hey, Landon, and yes, SolidWorks is accelerating everyone's hair loss, not just yours. You see all this? This is because I use Shaper 3D and NX. I'm 38, and I got this lettuce. It's from not using SolidWorks. Asterisk, that's not an official endorsement. Shaper 3D officially does not prevent hair loss. Yada, yada, yada. So we actually want to pick up the inside of the surface because we want to make it machinable, obviously. Obviously, because really, you know, machinists would argue that's really the only point of an engineer, is to give them things that they can make. And I don't disagree with them. There are many ways to look at the role of an engineer, and I mean, you know, you could. It depends on how you approach it. You could say the role of an engineer is to single-mindedly focus on producing manufacturable drawings. To me, that is not necessarily untrue. What's defining that? A machinist would say that, well, actually, no, that's what a machinist would say. The role of an engineer is single-mindedly creating manufacturable drawings and leaving the machinist alone. Okay. There's a wrong way to do this, and we're not doing it the wrong way. So a common mistake engineers will make earlier on in their careers, they will say, well, actually, this is not orthogonal to the outer surface, so you should, you know, use the wrap tool or whatever, and they would be right in the sense that it isn't orthogonal, but the machinist does not care. The machinist wants to make it super simple. And super simple is not having to chuck this part onto a 3 or 4 axis lathe or whatever it is, and instead just machine it from the top like this. And we don't really care. We just want that geometry roughly. So, and we are still having a little bit of interference, so gotta check that. How do we fix that? We have to set this off a bit, which we can do. See, this is why having accurate CAD is fantastic. because you can catch stuff like this. So all we have to do now is add essentially a feature down here that locates this off a little bit. So what will we do here? We're going to just move, we'll give it a 3 millimeter gap, we'll say. But we want the locating feature to stay. So how do we do this? We move this 3. And we will sketch on this surface and we'll just set some arbitrary, call it 20. Nope, not 20, 15. 15 millimeter sort of standoff, which, picked the wrong surface. Now we can create that standoff. Nope. Give me the number. That's my number. Okay. Perfect. Okay. So now you can see that the encoder is located nicely here. It's located radially, and then we have a little bit of gap to get the cabling through, which is great. Fantastic. And now that I'm looking at this, I'm realizing that this surface is on the nominal here. And I think we did adjust this a little bit, but I think this is making me a little uncomfortable, so I'm going to actually step back a bit and change the original before we copied it so that we can adjust both accordingly. So I'm going to pull back in time prior to that move copy. Okay, and we're going to adjust this down to, call it 8.5. Yeah. Okay, so that should adjust both. Parametric modeling. I was so anti-parametric modeling, you know. And I realized I disliked parametric modeling because of how it was forced on me. Parametric modeling has a place in engineering. The problem, as you can see, is that it's not for everything. So this actually just broke, and it isn't this CAD program's fault. The fault is in just the way that the paradigm of parametric modeling has been set. So, and fundamentally what it boils down to is parametric modeling doesn't really work because you don't know what you're going to design. If you know exactly what you're going to design ahead of time, parametric modeling works. When is that the case? Well, I can tell you confidently, I've never actually worked on any program in my entire career where I knew exactly what I was going to make at the end. And I've worked in consumer electronics, aerospace, entertainment. So anyways, enough ranting. Let me tell you when parametric modeling works. Parametric modeling works when you know exactly what you're going to make ahead of time. So if you have highly productized, if your product line is incredibly mature and you benefit from parametric modeling, then yes, go parametric model. So even in entertainment, I found instances where actually parametric modeling did work. Like, okay, if we're designing, trussing for this rotating stage. Well, the trussing follows kind of this this very easily defined sort of. There are systems in place that determine the size of that truss, and so you can actually you can make that parametric because You know what those things are going to be. You know, it's like, okay, this is at 1 foot intervals. So that's actually very easy to go make parametric. And then it's a product. So you can actually define 10 products off of that one parametric model. That makes sense. Where it doesn't make sense is, hey, I'm going to go design a robot, or I'm going to design a phone, or I'm going to design a spacecraft. I know roughly what it's going to look like, but I don't know down to each definition of each hole what it's going to look like. Parametric modeling doesn't work there. And 99% of engineers disagree with me on this, and that's fine. You know, I've just accepted that I'm going to disagree with everyone on that. But it's my strongly held opinion, and I have not been convinced otherwise. So if you know exactly what you're going to build ahead of time and parametric, and you're going to have multiple of a thing with slight variations, then parametric modeling makes sense. So if you're designing bolts, screws, nuts, trusses, decks, joists in a building, that actually makes sense. That can all be parametric. But if you're designing a rotary double inverted pendulum for the first time, you really don't need to parametric model it. End of rant. Thank you for coming to my TED Talk. Oh, and if you don't agree with me, please reach out to me and argue with me, because I'm desperately wanting to be wrong about this, and I desperately want someone to convince me. But I've spoken to the CEO of Autodesk. I've spoken to the CEO of Shaper 3D extensively. I've spoken to Blake at NTOP, and no one has convinced me. And actually, I don't know that Ishvan at Shaper 3D necessarily disagrees with me. We haven't actually really talked about it because I think he has better things to do, like build a company. Make this CAD great. That's what he's doing. Okay, there we go. So what happened to my screws here? They're still there, right? Yeah, okay. Okay, that looks about right. Landon, I am sponsored by Shaper 3D. It's right here. CAD, Shaper 3D. I am sponsored. Also sponsored by Send Cut Send. The piles of metal you see behind me are possible only through Send Cut Send. So, highly recommend those two services, obviously. Yeah, Shaper 3D is awesome. I realized that they were going to win CAD when I heard Ishvan. Well, I've known Ishvan now for a year and a half, about. But I really knew when I heard him talk about the product with his product team. And it sounded like I was listening to Steve Jobs' ghost, except Steve Jobs, but was actually technical, because Ishvan has got like a master's degree. He wrote a thesis, and he wrote a physics thesis, I think, for his master's or something, and like knows this stuff inside and out technically. So, but the passion for the product was equivalent to Steve Jobs. It's crazy. Now, when you talk to any other executive in the CAD space, none of them have actually used the product, so they don't actually really have anything interesting to say about it. I mean, just go use any product. Like, use FEA from, I mean, even the startups right now in FEA are pretty bad because they're just following the existing paradigm. Like, go find me any FEA package, especially go into startups and look for an FEA package, or, you know, the more modern ones like SimScale, and show me side by side what that product looks like. And I guarantee you it's exactly this. It's, hey, here's your model set up. You know, maybe it has a slightly fancy UI, but, and it's because they don't use the product, right? Like, they don't know what they've suffered through, what engineers have to suffer through. The same is true for SolidWorks. Like, I don't think John McKinley or whatever his name is ever actually was an engineer enough to understand what that product needed to be. Everyone coalesced around that design of the product because that product, the product became ubiquitous. And it wasn't a matter of it was good. It was a matter of, well, all my suppliers use it and I need them to be able to open my models. Right. And then once they became the incumbent, everyone else started doing CAD the way they did because they wanted users to feel comfortable. And then they just got into the self-fulfilling prophecy of crappy CAD. And it took someone like Ishvan at Shaper 3D to say, well, my dad was an architect or an engineer or whatever, and I know what he hated. And, I got my thesis on this stuff, and we don't have to build it like everyone else did. Same thing with Jim and Senkan-sen. Like, these people, they work from the customer back, which sounds trite, but it's true. It sounds trite, but it's absolutely true. Jim is like single-mindedly focused on getting delivery times down. And it's like, as a customer, it's like cost and delivery time. That's really how I see the world. For CAD, is it easy to use? Does it not crash? And is it fast? It's like, okay. Those are the 3 parameters you should be thinking about. Here, I'll give you an example. SolidWorks 2025 release features update. Let's look at what they did in the last year. Okay, first I have to click that button. No, let's find the press release. What's new in SolidWorks? Let's go. You had 12 months to design and develop your CAD package with $1 billion in revenue. And you have how many engineers? Let's talk about what you did in the last year. All right, let's go. All right, I see this long document. It's got how many pages? All right, well, it must have been a lot because you wrote 350-ish pages about your new features, right? Is this just like no, this is the what's new. So first problem, you spent how much time writing this document instead of actually making the product better? That's your first problem. So let's see. Let's look for new features. Oh, 3D experience. Okay, that's not new. SP4. Okay, your service packs shouldn't really be talked about here, but task scheduling. If you're an engineer and you're listening to this, how badly have you wanted a task scheduler? Exactly. Auto-generate drawings. That's actually a cool feature, but it doesn't work. I know it doesn't work because it doesn't have MBD, so you can't generate drawings automatically. See, here's what I'm talking about. Like, the managers at SolidWorks don't even know that they can't release the features that they're releasing. How are you going to auto-generate drawings if you don't have built-in MPD with every single license that you sell? You don't. So you can't auto-generate drawings because you don't know what my datums are. You don't know what my critical features are. You don't know any of that. Okay, so that's straight up a lie. So let's keep going. Stamping drawings with emails. Fantastic. Cool. Okay, I don't see any new features yet. Sheet set manager. Okay, AutoCAD's had that for 40 years. Let's see. Let's keep going. We're only at page 40, so synchronizing the title of single physical products. So essentially, they have a bug release report that's been rebranded as a feature release. That's what I'm looking at right now. I mean, are they not embarrassed by this? Task pane. Okay. Nope. Performance. Okay. Yeah, I want performance. That's good. But I wouldn't call that a feature update. I would call that you fixing the software. Reorganize components. Here we go. Reorganize components. SolidWorks. By the way, I'm so heated about this because I had to suffer. Like, I was paying a college to give me an engineering education, and I had to suffer for days instead of studying my, heat transfer work because I couldn't get SolidWorks to work properly. Like, this stuff is a blight on the world, literally. Like GDP goes down the worse the software gets. That's why I'm so heated about this. And no one in these companies care. Place component just below the part. This is nonsense. Like, no one's asking for this. Hole wizard has existed forever. Usability, that's not a new feature. Sketching, okay. None of this is new. All right, I'm getting off topic. I'm sorry. I'm so heated about this because it's just, yeah. My opinions, by the way, are not represented by Shaper 3D. I should say that. You know, they're not officially represented by Shaper 3D. Those are my opinions. Yeah, the reason I sound so heated about that is because it genuinely makes the world a worse place. Like, it really is, and it's not an exaggeration to say that. Imagine if tomorrow every nail gun and hammer in the world got 50% worse. Like, what would that do to the world? House prices would continue to skyrocket. Yeah, I hope that makes sense. I'm going to stop ranting about software now because I'm a mechanical engineer. Sorry about that. You can tell that I feel very deeply about the engineering software space. You know what? I should say something positive, and not just about Shaper 3D. So Shaper 3D, I love obviously because it's fast. I would not have been able to design this as quickly as I have. Here's something positive. A good example of a company at least trying something new is Zoo. At least Zoo is approaching it from a code first perspective. Do I agree with code first? No. Do I believe in parametric modeling? Not really. But at least they're not approaching it the way that SolidWorks and the incumbents did. At least. If the GPU performance thing works out for them and BRAP doesn't natively just make that impossible, then heck yeah. But at least they're doing something new. I respect that. And I just see so many startups in the engineering software space just selling me the same thing that's been done before. And a lot of this stuff doesn't even feel real. Like, I'm looking at, I don't want to name any companies right now, but I've reached out to founders in the last couple of weeks selling, raising huge amounts of money, which is great. The fact that VC is actually putting money into engineering software I think that's a great signal. But I've reached out to them to find out, like, what are you actually doing? Because, parametric modeling doesn't work. What makes you think organizational, what makes you think building software around that paradigm, any of the paradigms that currently exist, is going to make things better? I get frustrated by that because to really build software in this space, you have to suffer through it. And I'm not saying 3 years at SpaceX and 1 year at Tesla. I'm saying you have to go suffer for a decade using this crap and know deeply that you have to distance yourself from that paradigm. Okay, now I'm done with the rant. The only company I'm calling out is SolidWorks. No one else. Okay, so I think this is actually working. So we can work down and just double check some things. Actually, before I do that, I did see an error here. So this is actually threading. This should not be threading. This should be plus nominal. That should be 4.1. So 4.1. Because we're not threading into this, we are just through holing this. Okay. Got my gap there. That looks good. Preload here. That looks good. Looks good. Okay. Let's do a sanity check and run through all of this. Also, did my stream just crash again? That would be very disappointing. I don't think it did. Okay, it didn't. Good. Okay. So let's do that sanity check. We have pendulum 1, which rotates the nut, which rotates with our cable, which then rotates within the slip ring. That works. This is fixed. The PCBA is fixed. That's fixed to this arm. That's all good. Great. Then we spin this around. And then so we have fixed in purple, fixed on the outer ring of the bearing, fixed on this plate, and fixed on this cup. We rotate this pendulum. We rotate the inner ring. We rotate this nut, which rotates the magnetic encoder target. And that's the end of the rotating assembly. This cup, again, was fixed. That's fixed to the PCB, which is fixed, and that's all good. We route this through now this pendulum. That's good. And then we have our final pendulum with our weight, which this weight is not actually separated. So now it is with our weight. Great. That's all good. So this is now done. One last thing to do, we have to check interference to see if this actually hits anything. So before I do that, I will save a copy. We are at 11. Okay. So let's rotate this down. Actually, before we do, I'm going to wipe history. Let's see if we interfere with anything. Yes. Okay. Glad we checked that, because that would have been very annoying to find out in situ. So this could hit this, actually. Or actually, maybe it won't. Maybe that's okay. If it deflects a bit, it might, but... and then but there is good news. This is actually short enough that we don't need a secondary frame here. So that's great. What you see here is what we're going to get. Now, here's a fun little thing, which is how do you do interference checks on moving assemblies? Now, if you spent, your $7,000 a year on SolidWorks, you would have to give them another $3,000 for one of their features, which does motion, and that's silly. That's slow. The fast way to do this is to find your axis of rotation, which is here, draw a section. Actually, here's an even faster way, and you can do this in any CAD. And again, we're answering the question of, does my assembly interfere? Take your bodies that you're worried about, copy them out, this body and this body, this body. Copy them out. And then you're going to slice the body that you're checking. We're going to slice that about the midplane, which is just through the middle of that. Turn that off. Now we're going to sketch on this, and we're going to pick up the axis that we're rotating about, which is the center of this pendulum. Just create a little axis there. And then you take the projection of the part, and then you revolve that. around that axis. So this is the interference body representing this part. And so as this rotates, and we'll make it red so we know what it is. So as this rotates, whatever is in this path is going to be interfering with your assembly. So we'll pull up modeling again. And so let's delete, well, we won't delete that, but as you can see, we're actually just kissing right here. So we're actually just getting away with this, which is nice, but it's a little too close. Yeah, that's actually a little too close. Because over tolerance, you don't know what that's going to be. And then this is also going to deflect a bit, and so you'll actually hit this. So how do we fix that? Well, we could move this entire assembly off, but I would not want to do that. And actually, we should do this again for this pendulum. Actually, no, we're fine because we know it's further away than this. So how do we fix that? Well, we can make this plate not custom. We can make this plate custom, which is, in other words, to say, hey, actually, you want, say, 15 millimeters of clearance. You just slice this with that clearance, and Bob's your uncle. You could say that. Do we want to do that, though? I really liked having this be the same plate. It's going to reduce cost. It reduces cost, but this, I mean, what? This costs like $10. Do I really want to spend 30 minutes of my time to save $10? I don't think the math works out on that. Let me not dox myself. I'm gonna have to dox myself. It's all right. We're gonna upload this part. $3. Yeah. Okay. $3 is definitely not worth 30 minutes of my time. So we're going to make this a custom plate. And that's okay. That is A-okay. So yeah, we slice that. It's that simple. But we do need to make it look cooler. So that's really important. Okay. Is 15 enough? I don't think it is. I'm giving myself an inch. No reason not to. We actually don't have any reason not to do that. So there we go. Cool. We have designed a rotary dual inverted pendulum. Now we get to optimize it a bit, which is the fun part. In addition to that, we're actually going to also add some ballast. Or the ability to add ballast, because If you don't, this thing is going to essentially become a really eccentrically loaded, and it's going to want to generate a ton of moment that's going to want to pull itself apart, specifically pull it off of the mounting base. So we want to fix that. Delete all that. That broke. Got to get this drive mounted too. Actually, I should do an interference pattern. All around as well. Yeah. Whoa, what'd I do there? That's not right. I accidentally filleted that edge. It shouldn't be. So let's find that. There we go. So actually, the ballast is going to be really simple. I'm just going to use steel plates. And I'll just leave the option to mount them over here if required, which we don't have to do. And I do want to rotate this 180, I believe. So yeah, let's add that ballast real quick. Oh, already had that put there. That's good. So let's give that a healthy radius. And we'll isolate this and draw our plates. Okay. Okay, and then we'll do another, actually an easy way to do this. I'm just going to be using the offset tool, I think. Yeah, I think the offset might do this. So we do, call it 2. And then we'll mirror this over here. I think that's fast. There we go. First things first, we're gonna extrude this out, and we'll use half. Well, it actually doesn't matter because we're gonna just go order what we need to make the ballast work. But so, what's the radius here? 4. And then we pull these holes through. What's going on there? Oh, this was a Boolean thing. I don't want that. Okay, now I can pull these holes through. Okay. And so technically we should be able to stack these. Actually, we'll use the pattern tool like we're supposed to. I rarely use the pattern tool, but here we are. The right way to do this, by the way, is to actually go calculate this mass and, do plus or minus 50% on that. But, sun cut sends fast. So if I have to, I will be able to just quickly get some hardware in. Now, that's 6. I actually don't see a reason to use 6. Actually, maybe I will use 6mm since I'm using it on the heavy duty stuff, so I'll do that too. Copy, aka steal. Get this in the right place. So and then what is my distance here? 25. Not really correct. Picked the wrong one. What's my distance here? That's the one I want. 35. What are we at now? 55. We'll call it 50 because I don't think we can get 55s easily. Actually, I need to do this the right way. And then this was nominally 55, so we're going to bring this up 5, which should be all right. What's the next one? Yeah. I won't tell if you won't tell. We do need to change these to 6, though. So that sketch needs to change. I did this incorrectly. I should have made them all equal. should have made them parametric. There's an example where you should make things parametric. Because then I could just quickly change that parameter and I'd have correct screw sizes. But you live, you learn. So I'm just going to quickly offset these. 6.1. Wonder, can I actually linear pattern this pretty quickly? I've had luck with this in the past when they're on nominal dimensions. Why is that looking weird? So, what is this? 50.55? 60. Just giving it a shot. I don't think this is the right way to do it, but it's actually 60 there. It's just that they've made the UI so nice on this that it actually makes this kind of tolerable. There we go. Okay. That ballast is not necessarily what we're going to use. It's just an option if in building this thing we realize. Or actually, we will go do that analysis later. We will go find out what ballast we actually need. I just want to get the design down first. And we'll dial this in. All right. Need some lightning features here. I think we'll put them, I guess, on the back side. Probably better on the back side. So let's do a shell of, call it 3 millimeters. That gives us that surface, and then we can start cleaning this out. What happened to my, how am I preloading that? What did I do? Oh yeah, I need that. This is fun. I love the shell tool. Shell and replace face are tools that I found out about, I don't know, maybe in the last 12 months, and they've just totally changed. Actually, shell I've used before, but I haven't. Shell I really started taking advantage of maybe a year or two ago, but replace face is what I've been really taking advantage of. It's a fantastic tool. So what happens when we do, why was this breaking? No, it isn't breaking. I think that's fine. We'll make this 5 because I'm a little nervous about 4. Why not? And then we can't really do anything about, we can't actually make that. So we're going to undo that. So how do you do that? How do you modify a shell that's kind of not working? Well, you slice it, and then you can shell just the stuff you really want. So where are we going to slice this to tune our shell? How about here? So we'll slice this, and then we'll shell just this body, and then we'll join it back in a second. So shell, I think we said 4. There you go. That's more manageable. And actually, let's get really cute with it and add a rib right here. I'll show you a nasty but fast way to do that. We want the center of this. How do we do that? Bear with me. This is going to make sense in a second. There we go. Then we slice this. Genuinely, what the team has done with the slice tool has been so incredible. Just nothing but respect for the speed with which they incorporated that as well. Okay, so we're adding a little rib there for some stiffness. We actually should add one here too. So, oh, that one will be easy. We can actually, I think we have a little bit of, we'll just draw that. We give ourselves the 4 that we did earlier. So 2 on each side. Okay. And to be good little engineers, we should also do this other screw hole up here too. Okay. All right. And then we fillet this so that they can actually manufacture it. So if you actually, we can actually slice this in 2 real quick to make this filleting operation faster. So if you were to try and make this, if you sent this for DFM, they would actually tell you to pound sand because you can't actually mill features like this without an internal radii. And generally speaking, you want that radii to be as big as possible. So we're going to go for 3 right now. It's not as big as it probably should be, but you know, we'll wait for them to come back and say they can't do it. And I don't know that we can get 3 on this one. We can. Fantastic. 3. So we'll try and do 3 all around. This one might be a problem. It kind of is. So let's see if this will... We'll have to sketch that one out. So yeah, and if you don't believe me, go look at an end mill and you'll see why you can't cut squares with an end mill. So now we're going to connect this, and this is a tangent. No, not a tangent. How are we going to do this? We'll just pick some arbitrary angle. I don't think it really matters too much. Make that 90, and then you can see this is going to be the path that they actually cut through. Let's see if we can find a way to blend it into this cutting path. That makes sense. Yeah, I don't think there's a pretty way to do this, so I'm just gonna settle for this. I don't really have a better justification for what I'm doing here. That doesn't look right. Spending a little bit too much time on this, but whatever. Okay. Pretty, no. Manufacturable, yes. So we'll give them a little end mill radius in the bottom here. And then we'll mirror this back. I'm going to send this to Pete for DFM, see what he says. He's probably going to tell me to go get a job. Okay. So that part is now, I guess, optimized. This arm needs a path cut so we can pass cable through it or wire through it. So how are we going to do that? I think we'll just kind of go with what feels right here. So we want the cable to be, I don't know, let's give ourselves an inch of, ooh. All right, not going to give ourselves an inch, we'll give ourselves half an inch of routing space. Actually, we're going to cut this. We're going to create a pass-through right here. Actually, no, we're not going to do the pass-through right there. We're going to do it up here. How thick is this? 6.35, so we'll bring this in, I don't know, we'll call it 3. Yeah. Yeah. Does this actually rotate? I think I'm going to do this instead. And then just cut a 1-inch pass through here. Roughly an inch. Too much, call it half. Roughly half. Okay. And again, we have a cable routing through there, so we want to break that hard edge. We'll want to add some routing down here. Why are you not giving me this edge? There we go. And how do we get cable? Oh no, the cable comes through here, so I don't really need to do a pass through. That's right. Okay, and then we actually do kind of want to cap this, I think. I think we want to cap that to prevent the cable from getting out. I think. Actually, overcomplicating it. That will get capped on tape, as every prototype should. Okay. All right. And then we'll route through here, and then, yeah, that cable just comes through here, and we'll have to make a cable guide maybe for that. Maybe that becomes a 3D printed part or something. Yeah, I'll think about that later. Actually, on that note, I should add some FET holes just in case we do need to do that. I don't want them too close to this area because that's actually going to be a hot spot for stress. So I'm just trying to keep it away from there a little bit. Not that I'm particularly worried about stress in this application. It's just, if you know something, if you know a better way to design it, then you should do it regardless of whether or not you've done the analysis to prove that it's necessary. And you can kind of see what I'm talking about here already. Like this, you can tell when I apply load here, the highest area of stress is going to be between these features. So really this should be even more. We should go back to 25. Yeah, to get it out of that area. So now we have this full section to resolve loading through. Okay, 17 it is. These FET holes aren't necessarily being used right now, but they do enable us later to be able to use them. And they're a little big, 4 millimeter. Yeah. Don't love it. Don't love it. I guess we are passing, yeah, never mind. We're passing stress through, we're passing load through this member here, so it's kind of misleading, so we're fine. Okay. I don't think this has to be as big as it is. It's just one cable essentially. Yeah, and that lets me bring these out just a hair. There we go. Cool. Okay. Just do some light modifications of stuff that we know can be better. We'll just go through each part real quick and just make sure that we're not missing any low-hanging fruit in terms of DFM stuff. So this one, can we have a radius there? Yes, we can. That looks good. Next part, plate, don't have to worry about that. Cup, do have to worry about that. And we don't have a radius here, so we should add that. Really, that should be 4.5 depth divided by 4.5. So that's 33 deep divided by 4.5, roughly 5. Just about 6 millimeters of radius there. Fillet, I should say, which is too much. So we'll negotiate with them down to 4. Let's see if they say anything about that. Should be fine. We want to break this hard edge, I think. It's going to get dinged up. Oh, we have lots of space there. We'll make that 1. Actually 2. Why not 2? Same story. We need, I think, an internal radius on this part. Oof, but it's got to be... Actually, we won't put 1 there. We'll see if they can give us just whatever the radius on that end mill is. So that's part is done. We said we don't care about this one. This arm now we can tinker. Okay. Looks good. Same deal here. I think we can add a radius there. That does 2 things. One is it frees up what they use for the mill. Actually, that isn't necessarily true, but it just signifies that, to me at least, that I can have a radius there. So if they say, instead of 3, can you get away with a 1 or less, I can say absolutely. But generally, it's best practice to, for a stiffness transition like this in a single part, have a radius there to help relieve stress. We just did this part, but let's sanity check it just in case. Looks good. Add a radius there just in case. This is the flexure, that sheet, we don't care. This one we do care about. Is it going to be problematic to... No, this is plastic, that's fine. Is this part of the actual encoder? Did I just design this entire thing with the removable... non-critical component? Hope not. No, that looks like it's important. It's a plastic standoff, I think. Right? I think it tells us here in this documentation. Yeah, that plastic cover might not actually be a part of the assembly. No, it says plastic spacer, right? Yeah, what is that? I mean, it looks like it's there. Yeah, that spacer is there. Yeah, it has to be because you bottom out the microcontroller and all that other stuff on the housing if you or on this part, or any part really, if you didn't do that. Oh, this needs some lighting hole love, I think. Yeah. Quick way to do that, slice it, shell it. Boom. We don't want this because it's not that critical. But we do want these, I think, or what we can get away with these. So see, can we do 3? Not really. Is this distance even 3? Yeah. I don't know a simple way to do this one. Four might be too much. We'll switch that to 3. No. Yeah, I don't care. It's too complicated. I'm not going to worry about that. So this part's done. This is sheet. Oh, we got to join that back. So this is sheet. So we don't care about that. No, that isn't sheet. That's the slip ring. So we don't care about that. These sheet, don't care. This is not sheet, but I don't think there's really anything we can do with that. This is, yep, already DFM'd this. Sheet, don't care. Oh, this was a unique part anyway, so. Okay. Cool. This is done. Oh, this is unique, so we can get rid of these features now, so. And then we want the base actually to be big. Because I want space to mount this essentially to a frame to keep this thing from flying around. Okay. So I actually want to make this rectangular, I think. But I will do that. All right, this is at a point now where I can go release parts for this. So I'm not going to bore you with that. I'm going to say this is done, and I'm going to go release parts. And then next time we will design the enclosure, because this is a kilowatt motor, and I did the math, and spinning this mass is roughly like moving a baseball at 700 miles an hour, something crazy like that, Mach 1, which is pretty scary. So we're going to build an enclosure to make sure that I don't throw a rotating double inverted pendulum through a window, or me for that matter. So, but that's it. I think this is done. This is what it looks like. I'll update the GitHub on that too. Pretty cool. Okay. Yeah.